Let's go over this final exam review. It's kind of lengthy, but it's a wonderful review. And in fact, every single problem on this final exam review came off an old final exam. So we begin at the top, number 1. This is really a calculation type question about sets. Okay, first one, we want to list some elements. But maybe as a side step, I will calculate b minus a because I see that here. So we start with b and we remove the elements that are also in a. So that would be removing just element 6. So b minus a is the set 3 and 9. Now let's jump into letter A. We start with c here, and then we remove the elements in b minus a. Well, you see, that's just removing element 3. So C minus B minus A is the set 4, 5, 6, and 7. Now we have some true false. Well, I want to say something about A intersect B, and I want to say something about A union B. So let's just write these sets, and then we can answer the true false. A intersect B, we take here and here. What's common to both? Well, this is just 6, the only element that is common to both. And A union B, well, I have 2, 3, 4, I have 6, I have 8 and 9. We can make sure 2, 3, 4, 6, 8, 9. Wonderful. Now this is quite straightforward to answer these questions. True or false? A intersect B is a subset of C. Yeah, this is true because here element 6 is contained in this set, right? Now, is C a subset of A union B? This one is false because, well, 5 is an element of C, but 5 is not an element of A union B. And similarly, 7 is an element of C, but 7 is not an element of A union B. Now for letter D, we can begin by listing the elements of B intersects C, maybe as a side step. And then the question is asking for the power set of B intersects C. B intersects C, just looking at the two sets, is the set containing 3 and 6. This is 3 and 6. Note that this has 2 elements. Therefore, the power set of B intersects C will have 2 squared or 4 elements. Power set. First of all, the empty set is a subset of every set. We have the singletons. And then we have the set containing 3 and 6. And this completes number 1. Number 2, we want to show here not P implies not Q is logically equivalent to not P and Q. And I have pre-drawn a truth table with all the columns that we need. Now, in the end, this column and this column should have the same pattern of T's and F's. And when we get that, we will know that this compound proposition and this compound proposition are logically equivalent. Okay, well, we have P can be true and false, and Q can be true and false. So we have 4 rows here in our truth table. The first thing we do is we negate P. This is false, false, true, true. Then we negate Q. This would be false, true, false, true. Okay, now we have an implication, and the implication is here. It's this implies this. If we remember, the implication is only false one time. It's when we have a T followed by an F. So this third row is false, and everything else is true. Okay, now we have an and. An and is true only one time, but what are we anding? We are anding this column and this column. And the only time the and is true is here you have 2 t's, and any other time it's false. So this is the third row is a t, and then this will be false, false, false. Okay, now we take this column here and we negate. So we switch all of the truth values. This would be t, t, f, and t. Now this is wonderful because here and here, well, you see we have logical equivalence. We just need a sentence to explain this. So as columns 5 and 7 have the same truth values, we see that this not P implies not Q. This is logically equivalent to not P and Q. And this is the end of number 2. Number 3, it's another truth table. We want to show that this compound proposition is a tautology. Tautology, well, it even says in the problem, this means a statement is always true. So I have put all of the columns that we need already. And again, P can be true and false. Q can be true and false. We have 4 rows in our truth table. What we're looking for to conclude tautology is here. We should see only T's, 4 of them. Okay, the first thing we have is not P. Now we have an OR. We are ORing this column and this column. And the OR is only false when they're both false. And you see that happens here in the second row. So this is the only time I have false. And then I have true, true, and true. Now I have an AND. I am ANDing this and P, which is here. Okay, so the AND, we need both to be true, for the AND to be true. And you see this happens only in the first row. So we have true, false, false, and false. Now the final step, we have an implication. We take this, implies this one, okay? So we're looking for this one time the implication is false. It's when we have a T followed by an F. Well, there's only one T in this column, and it's followed by a T. And so you see that's true, right? Here, T followed by T is true, but also having false followed by anything is true. Now we see we have a tautology. As column 6, I'll just say has 4 T's. We see that this, it's P and not P or Q implies Q is a tautology. And this is the end of number 3. Number 4, we want to find the coefficient of x to the 5th in the binomial expansion of this, x plus square root x to the 8th power. We will use the binomial theorem here. And the binomial theorem says the following. It says that x plus the square root of x to the 8th power, well, it's a sum. And this would be a sum, k equals 0 to 8. We have 8, choose k. Let's see, I can write it this way, x to the 8 minus k, and then square root of x to the k, right? Now, let's do one more step here and combine this into a single power of x. So this would be a sum, k equals 0 to 8, 8 choose k. This, okay, here, this part, power to a power, we multiply. So this is x to the 1/2 k, and then we can add the exponents. So this would be altogether, we have x, this would be 8 minus k plus 1/2 k. And, well, I could take one more step. You see, altogether we have x to the 8 minus 1/2 k, which I'll write that in the next step. But what do we want here? Well, we want this power, 8 minus 1/2 k, to be equal to, we want the coefficient of x to the 5. Now you see we can solve for k. We get minus 1/2 k is minus 3, and this gives us k as 6. That's the term that we want. And so the final answer here, the coefficient, this is 8 choose 6, which you can also write as 8 choose 2. And this is 8 times 7 divided by 2, which is 56 over 2. This is 28. This is our final answer. Number 5, combinatorial proof. We want to prove this identity combinatorially. Well, there's a few ways you can do this. I will just start with a set with n elements. So let's let A be a set with cardinality n. Now, what I want here is I want two disjoint subsets. Cardinality of C is K, and cardinality of D equals L. And what I will claim is that both the left-hand side and the right-hand side count the number of pairs of this type, number of sets C and D that satisfy this. They are disjoint, cardinality of C is K, and cardinality of D is L. So we may count the number of sets of this type as follows. Well, way number 1. First, well, this will be the left-hand side. First, let's choose k elements from A for set C, and then out of the remaining n minus k elements of A, we want to choose L for set D. And this is multiplication rule. Well, we started with n elements, we chose k. Out of the remaining n minus k elements, we chose L. And so we have this product here. And this gives the left-hand side. Now, way number 2. Well, we can count as follows. It's another way to count the exact same thing. This is the idea, the whole idea behind combinatorial proof. So we choose k plus L elements from A for C union D, because we are going to make them disjoint. So their union will have k plus L elements. Then out of the k plus L elements, we can choose L for set D. Now, maybe I'll put this as a comment. The remaining, this is just a comment really. You see we have no other choices because the remaining k elements are for set C. out of the k plus L. So first you choose k plus L for the union, and then you specify L of them for set D, and then just the other k go to set C. Again, we have multiplication rule. Gives out of n we chose k plus L, and out of k plus L we chose L. Subsets. We have shown the left-hand side and the right-hand side count the exact same thing. It's the number of here subsets of A, C, and D that are disjoint, and cardinality of C is K, cardinality of D is L, and so therefore we have proved n choose K times n minus K choose L equals n choose K plus L times K plus L choose L. This is what we were trying to prove in this combinatorial proof. Number 6, for integer x, we want to prove if x squared plus 1 is even, then x is odd. Let's see. To me, this would be the easiest, thinking contrapositive. So that is what we will do here. We assume x is even. And we want to show that x squared plus 1 is odd. This is exactly the contrapositive. Contrapositive of a statement is you negate this, implies you negate this. So we assume here that x is even. We will show here x squared plus 1 is odd. Definition of even, there exists an integer with x equals 2n, and then, well, x squared plus 1, this is quantity 2n squared plus 1. This is 4n squared plus 1, which is 2 times 2n squared plus 1, which is odd as 2n squared is an integer. And this completes number 6. Number 7, this to me is another contrapositive. It says the following: we have integers a, x, and y. If a does not divide x times y, then a does not divide x, or a does not divide y. We assume, well, this time we have an or to negate here. And when we negate an or, this becomes an and. This was De Morgan's. So we assume, well, we have integers, very nice. But here it says a does divide x and a does divide y. And then I want to show that a divides this product, xy, okay? Well, really, I only have to use one of these. I will use that a divides x. There exists an integer with an equals x. Okay, I want a divides the product x times y. So let's just multiply both sides by y. And I can group like this here as ny is an integer. We see that a divides this product. This is the end of number 7. Now for number 8 and number 9, you see these are both contradiction. And when we have a proof by contradiction, we assume the statement that you're trying to prove is false. Argue until you reach a contradiction. in this case, we assume there is a smallest rational number greater than 1. And we can, let's say, call it x. Okay, so x is now the smallest rational number greater than 1. Now, x is a rational number. Moreover, x is positive because it is greater than 1. And so we can find, I'll say this, natural numbers with x equals m over n. Okay, we're guaranteed definition of rational number that m and n are both in Z, and n is not equal to 0, but because x is positive and in particular also bigger than 1, we can find natural numbers m and n with x equals m over n. What I'd like to do is contradict this word smallest. So we need to create a rational number that's bigger than 1 but is smaller than x. Okay, so let's just think about this for a moment. How can we create such a number? Here's a number line. Okay, we have 1 and we have this number x. How can we find a number that's strictly between the two? Well, we could just take halfway in between, right? This would be bigger than 1. This would be less than x, but we need to argue that it is a rational number. And to get halfway in between, we would just take 1 plus x divided by 2. So let's do this now. So we consider, I will call this y, which is 1 plus x over 2. As x is bigger than 1, we have that y sits between 1 and x. Moreover, we need to justify why little y is a rational number. And so we can just add, this is 1/2 plus m over 2n, which is n plus m divided by 2n. And this is a rational number these are in fact natural numbers, but I'll just say in Z, and 2n is not equal to 0. And so we have our contradiction. This contradicts that x was the smallest rational number greater than 1. And this is the end of this proof by contradiction. Like I said, we were contradicting this word right here, smallest. Number 9. Again, contradiction. We want to prove there are no integers a and b with 3a minus 9b is 2. So by contradiction, we assume we do have. So we assume there exists a, b integers with 3a minus 9b equals 2. Well, in this case, we may just factor out a 3. So we have 3. A minus 3b is 2. And then as a minus 3b is an integer, we see that 3 divides 2. However, we know 3 does not divide 2. We have a contradiction. And this is the end of this proof. This one was a little bit shorter. 3 divides 2 and 3 does not divide 2 provides our contradiction. Number 10. Well, you see we have a set-theoretic proof we also have an if and only if. So this will be fun. Let me label some things. I will call this P and this Q. So for sets A and B, we want to prove A is a subset of B if and only if A minus B is empty. Now, we have some choice here. I think I will do both directions by contrapositive. So the forward direction, which I will do first, would be this. It would be P implies Q. But by contrapositive, well, you assume not Q, namely that A minus B is not equal to the empty set. And we want to show that A is not a subset of B. This would be not Q implies not P. It's the contrapositive, like I said, of this direction. Okay, well, A minus B is not empty. That means there exists, say, some Y that is in this set difference. Now, we can unravel A minus B. This says Y is in A and Y is not in B. Well, you see, we have proved what we want here. Therefore, we can conclude A is not a subset of B, because if we go back and remember, this means for all X is in A implies X is in B, right? And we found a specific, I called it Y, that is in A and not in B. And therefore, that's precisely what not subset means. So we have proved this forward direction by contrapositive. Now, we want to prove Q implies P. And I mentioned I will also do contrapositive here. So Q implies P by contrapositive, we would assume that A is not a subset of B. And we want to show that A minus B is not empty, right? This is not P implies not Q, which is the contrapositive of Q implies P. Well, A is not a subset of B. It's almost the same argument that we did in the forward direction. There exists an X in A with X not in B. And then we can say that X is in this set difference, meaning that A minus B is not equal to the empty set. And this is the end of this direction. It's also the end of this if and only if proof. I proved both directions by contrapositive. Okay, now for number 11. We have another set-theoretic proof. First of all, we have set A, B, and C. Part A, we want to prove that C is a subset of A intersect B. So let's let, say, Y be an element of C. We need to show that Y is in A and Y is in B. And then we can conclude Y is in the intersection, A intersect B. Well, let's use the definition. There exists an integer with 24n equals y, because that's what it means to be in C. C contains, well, you could say all multiples of 24 or all integers x such that 24 divides x. And that's precisely what this is saying here. I'll just say notice. We may write 24 as 4 times 6, and so 4 times 6n equals y, and as 6n is an integer, we see that 4 divides y. Now similarly, we have 6 times 4n is y. As 4n is an integer, we see that 6 divides y. Okay, so 6 divides y means that y is in A. 4 divides y means y is in B. So y is in A intersect B. And this is the end of part A. We want to show C is not equal to A intersect B. Well, you see, we have subset in one direction. And so for not equals, it means like this. So we need to find an element that's in A intersect B, but is not in C. Just looking at this, I will say notice 12 is in A intersect B, as 4 divides 12 and 6 divides 12. But 12 is not in C, as 24 does not divide 12. And this is justification. Thus, C is not equal to A intersect B. This is the end. That was the end of part A. And part B, okay, here. This is the end of number 11. Number 12, we move into induction. We want to prove here, if we add up j equals 1 to n of 3j minus 1, that we get this 3n squared plus n all divided by 2. We will prove this by induction. Every proof by induction has a basis step and an inductive step. So we begin, the basis step is typically a verification. This is for n equals 1. And here, the left-hand side, there's only one term in the sum. It is 3 times 1 minus 1, which is 3 minus 1, which is 2. Now, the right-hand side, when n equals 1, we get 3 times 1 plus 1 divided by 2. This is 4 over 2, which is also 2. Okay, so the left-hand side and the right-hand side are both 2. We have completed the basis step. Now for the inductive step, we assume k is a natural number, and, well, if you add j equals 1 to k of 3j minus 1, we get 3k squared plus k, all divided by 2. Now we want to show that this holds for k plus 1. So if you sum j equals 1 to k plus 1 of 3j minus 1, we get, well, the right-hand side for k plus 1 is as follows: 3k plus 1 squared plus k plus 1, all divided by 2. Well, I want to work with the left-hand side until I get to the right-hand side. And I know that I want to use my inductive hypothesis. So let's write the sum of the first k, and then we will write the k plus first term here, which is 3k plus 1 minus 1. Okay, here's where I use my inductive hypothesis. It's right here. It is that this equals, well, we see it 3k squared plus k divided by 2. And then we still have this other part, which I can simplify to 3k plus 2. This was by my inductive hypothesis. Now I can look at where I'm trying to go. I want here some expression all over 2. So let's get a common denominator. This would be 3k squared plus k, and then I have 6k plus 4 all over 2. Now again, you see, let's pull off a k plus 1. This would be 3k squared plus 6k plus 3, and then plus k plus 1, okay? All over 2. Now you see this part is exactly 3 times k plus 1 squared. Okay, so this equals, we have 3k plus 1 squared, and then plus k plus 1 over 2. This is exactly what we wanted in this proof by induction. This is the end of number 12. Number 13, we have a recursively defined function. We will use induction here as well. We are told the following. We are told a 1 is minus 1, and then for n bigger than or equal to 2, we have this. an is 2an minus 1 plus 3. We want to prove that an has this explicit formula for every natural number n. Okay, this again by induction. Our basis step, I will put here. This is verification for n equals 1. Well, we are given a1 is minus 1. If you think about this, this is 2 to the 1 minus 3. And so this checks out. This formula for an works for our n equals 1. Now, next comes the inductive step. We assume k is a natural number with ak equals 2 to the k minus 3. We must show that ak plus 1 equals 2 to the k plus 1 minus 3. Okay? And, well, we're going to use our inductive hypothesis and use the recursion, of course. So we have the following, that ak plus 1, this equals 2 ak plus 3. This was not the inductive hypothesis. This is this defining recursion. This is 2. Now I can use my inductive hypothesis. AK is 2 to the k minus 3, and then I have plus 3. And then this is 2 times 2 to the k minus 2 times 3 plus 3. Well, 2 times 2 to the k is 2 to the k plus 1. And this is minus 6 plus 3, which is minus 3. And you see, this is the end of this proof by induction. We have finished. Number 14, we are moving into relations and also functions, as we will see. Okay, well, we have a relation on A, this set here, defined as follows. X relates to Y if and only if X equals the absolute value of Y. The first thing we want to do is list the elements of R. So here is part A. Well, you see, this is the first coordinate, and each ordered pair is the X, and X needs to be absolute value of Y. Well, we have, for example, 0, 0, 1, 1, we have 2, 2, we have 3, 3. But there's more than this. We have also 1 minus 1, 2 minus 2, and 3 minus 3. But you will never see a negative number in the first coordinate for this relation. So this looks good. This is R here. Okay. Now, B, true or false? R equals R inverse. Immediately we know this is false. Because, well, this is definitely not symmetric. And if you interchange the coordinates, you will see the negative entries in the first coordinate, and that does not happen in R. Letter C, R is reflexive. This also is false. Because, well, this contains 4 of the elements of the form, say A comma A, where A is an A, but not all of them. So this is not reflexive. It does not contain minus 1, minus 2, minus 2, or minus 3, minus 3. Now D, how can we get our brains around letter D? Well, you can look at the ordered pairs. We could draw a picture. 0 relates to 0 here. 3 relates to 3. 2 relates to 2. 1 relates to 1. And then we have 1 relates to -1, 2 relates to -2, and 3 relates to -3. So this is the picture of this relation, okay? Now, if we look at this, right, to be transitive, we would need, if you have two sides of a triangle, we must have the third. There's no problem here, right? You don't ever have sort of two sides of a triangle where you fail to have the third. This is transitive. Part D is true. 15. This has A, B, C, and D. We'll do A and B on this page and then move to the next for C and D. We have the exact same set and we're asked, is it an equivalence relation? Also, is it a function? So I'm going to draw pictures for both. So we have these two different pictures. One is really, if we think about relations, one is if we think about functions, but I am going to think about them both ways, so I will draw both pictures. 1 relates to 1. We also have 2 relates to 2. We have 3 relates to 3. And then we also have 1 relates to 2, 2 relates to 1, and that's it. Okay. This looks wonderful. This looks symmetric. This looks transitive, and this is definitely reflexive. So part A, this is true. We can think about this looking at the picture. Now, letter B, let's think about this in the function world. Well, we have a lot going on.
1 maps to 1.
2 maps to 2, 3 maps to 3. This would be a function, but there's more. 1 maps to 2, 2 maps to 1, and this is it. Now, look at this. Is this a function? No, it's not. So part B is false because elements 1 and 2 have 2 arrows coming out of them. This is not a function. Now for C and D, you see we have the same set A, and I just recopied these pictures. This is thinking about in the relation world, and this is thinking about the function world. Okay, well, we have a different relation here. 1 maps to 2, 2 maps to 3, and 3 maps to 1. Well, without a doubt, C is false. This is not reflexive, for example, okay? So this is definitely problematic. It's also not transitive. It's also not symmetric. All 3 of the properties for equivalence relations fail. But if we move over here into the function picture, 1 maps to 2, 2 maps to 3, and 3 maps to 1. This looks wonderful. Part D, this is true. This is a function. Okay, every element in the set 1, 2, 3 has exactly 1 arrow coming out. Okay, 16. This is similar, I will say, to some we had on our test 3 review, but we have the set A, which is the letters M-A-T-H. We want to find a non-empty relation R, which is symmetric and transitive, but not reflexive. So we cannot add all pairs, MM, AA, TT, and HH. As long as we don't do that, it will be not reflexive. So I have lots of options here. I can just have it be 1 ordered pair, AA, like this. That's one option. I could add more. For example, a more exciting example perhaps, if I add MM, AA, and then I can add MA and AM. This is another example. Of course, this just asks for 1. And so either one of these is perfectly fine. But either one of these, maybe I should label this R1 and R2. This would work and this would work. Either one of these, R1, R2, or many, many other possibilities, satisfies symmetric, transitive, but not reflexive. Number 17, we have a function. Domain is z cross 0, 1. Codomain is z. And the formula is here. F of nm is n plus 2 to the m. We want to prove or disprove. F is 1 to 1. Prove or disprove. F is onto. And then we will make a comment. Is F a bijection? Well, let's see. We will disprove 1 to 1. And we will prove F is onto. Now, before I even do that, we will be able to answer no in C because bijection means both 1 to 1 and onto. Okay, well, let's get started with part A. How do you prove, well, how do you disprove a function is 1 to 1? We need to find two elements here in the domain that map to the same element in the codomain. So let's consider the two elements I will choose is 0, 1 and 1, 0. These are both in Z cross 0, 1. We have the following. Let's evaluate F of 0, 1. This is 0 plus 2 to the 1, which is 2. And F of 1, 0, this is 1 plus 2 to the 0. This is 1 plus 1. This is also 2. And so you see F of 0, 1 equals F of 1, 0. But these 2 points in the domain are not the same. And this justifies that F is not 1 to 1. Now for B, I have told you we are proving onto. Well, what we need to do is take an element in the codomain, and we need to find an element in the domain here that maps to it. So let me think for a moment. Okay, here we go. I'll say notice we can take n minus 1 comma 0, and this is an element of Z cross 0, 1 with, let's evaluate F of n minus 1, 0. This is n minus 1 plus 2 to the 0, and 2 to the 0 is 1, so this is n. Hence, we have proved that F is onto. Okay, now part C. As I mentioned, this is very straightforward. Since we have already answered A and B, the answer is no. F is not a bijection because F is not 1 to 1. And this is the end of number 17. Number 18. Okay, part A. Well, we're given a sets A and B. We want two functions. One is a 1 to 1 function from A to B, and one is an onto function from B to A. I will list these with ordered pairs. From A to B, 1 to 1. Okay, so let's say 1 maps to 3 and 2 maps to 4. Okay, that's certainly 1 to 1, and it's a function from A to B. And now I need an onto function from B to A. We'll say 3 maps to 1, 4 also maps to 1, and then say 5 maps to 2. Okay, so here is an example of an F and a G that we need in part A. Now part B, we want to find G-compose F. Here, F happens first. So I will give the domain and codomain. The domain of G-compose F is the same thing as the domain of F. So this will map from A. F maps A to B. G maps B to A. So the composition will go A to B and then B to A. This will be a function from A to A. Okay. And let's write the ordered pairs. 1 maps to 3, 3 maps to 1. So we have 1 maps to 1. 2 maps to 4, 4 maps to 1. And that's all there is because we have domain A. Okay, letter C. Now, the answer in C is very specific to what we chose in A and hence in B. So we look at our specific function, G compose F, and we ask, is it one-to-one? Is it onto? No and no. So G compose F is neither one-to-one nor onto. We can see this from here, this function definition. Number 19, we have functions f and g. And the question is, if f and g are one-to-one, then the composition is one-to-one. And we know, just as a comment, G compose F, in this case, maps A to C. Okay. This is very similar to something we had in our test 3 review. So let's prove this. Let's assume we have sets A, B, and C. We have F from A to B, and G from B to C are one-to-one. We want to show that G compose F is one-to-one. And how do you show a function is one-to-one? Well, you take two elements in the domain with the same function value. So G compose F of X equals G compose F of Y. We need to show, in fact, that X equals Y. This will show that G compose F is one-to-one. Well, we have, if we use the definition of the composition, that G of F of X equals G of F of Y. Now, G is one-to-one. And so we have that F of X must equal F of Y. And now we use that F is one-to-one. We get that X equals Y. And this is exactly what I wanted to show. So this is the end of this proof. Number 20, we have set A, which has 3 elements, set B, which has 4 elements, and we are counting functions. We could have started with a preliminary, just how many functions are there from A to B or from B to A, for example. We will address that a little bit in part C. But letter A, this asks for one-to-one functions from A to B. So I can construct a function from A to B, thinking about it as a list of length 3, where all I need to do is specify f of 1 and specify f of 2 and specify f of 3, and then I have a function. But this is one-to-one. And so I have 4 choices for f of 1. Once I have selected that, I can choose to make a one-to-one function any of the other 4 except the one I have chosen. So I have 3 choices here. And similarly, I will have 2 choices here. So altogether, let's see, what is this? 12 times 2. We get 24. Or you could write this as P for 3, for example. Or, well, we also see this is 4 factorial, because if you just multiply this by a 1, we see exactly 4 factorial. Okay, well, these are all 3 different options for this quantity. Letter B. One-to-one functions from B to A. Well, you notice the cardinality of B is bigger than the cardinality of A. So the answer is 0. This came from pigeonhole principle, really. But also, if you tried to do multiplication principle, we would have a list of length 4, where you have 3 possibilities, then 2, then 1, and then actually 0, and multiply. We would get 0. But this really came, as I mentioned, from pigeonhole principle. So these are our answers so far. Now, letter C. Onto functions. Let's remember how we did this. This was inclusion, exclusion. Okay, so let me define some sets here. We can say C1, C2, and C3. This is all we want B to A. So F from B to A, such that 1 is not in the image of F. And then this would be all F from B to A, such that 2 is not in the image of F. And finally, C3 is all functions from B to A, such that 3 is not in the image of F. Okay? Now we want onto functions. We can think about a Venn diagram here where we have 1, 2, and 3. This is not an accurate Venn diagram. It is just a picture. We have C1, C2, C3, and our universe is all functions from B to A. So the cardinality of U, all functions from B to A. Well, you can think about this as a list of length 4, where you have 3 possibilities in each spot. So the cardinality of U is 3 to the 4. Now, you see what we want, and this was in our inclusion, exclusion video. We want everything out here. This is all of the onto functions, because anything that is not onto is in the union of C1, C2, and C3. So anything not onto is here. Okay? Now, from this point, it is not too terribly hard to calculate. You see the cardinality of any of these, C1, C2, or C3. Well, you have a list. In fact, I can add this here. We have 1, 2, 3, 4. For all functions, we could put all possibilities from elements in A. But for any of the CIs, you see, you only have 2 possibilities. So for the CIs, you have 2, you have 2, you have 2, you have 2. So the cardinality of any of these is 2 to the 4. Now, if you take here, cardinality of, say, CI intersect CJ, where I and J are not equal to each other, say I not equal to J. Well, let's think C1 and C2, okay? That would say 1 is not in the image, 2 is not in the image, and how many functions are there? Well, you see, if you go back to this, thinking about a list of length 4, there's only 1 element. And if it was C1 intersects C2, the only element the function can map to is element 3. So you would have this. So this is 1. Okay. And then finally, if you take all 3 of them, C1 intersect C2 intersect C3, well, this is why I said this Venn diagram was not accurate. It was just a general picture. This would say 1 is not in the image, 2 is not in the image, and 3 is not in the image. Well, there are no functions like this. So this is 0. Okay, now we have all the pieces we need for inclusion, exclusion. So the total number of onto functions, we'll put down here. We would take the cardinality of U and then minus, well, we would have cardinality of C1 plus cardinality of C2 plus cardinality of C3. There's 3 of them, and each one has cardinality 2 to the 4. And then we subtract off the cardinality of the intersections. There's 3 intersections. 3 choose 2 is 3. And each one has cardinality 1. And then we add back the cardinality of the intersection of all 3, which is 0. And finally, we can do this. This is 81. This is minus, here we have 3 times 16 minus 3. This is 45. Altogether, we get 36. So this is the number of onto functions from B to A, and it used the inclusion exclusion for 3 sets. This is the end of the final exam review, and thank you very much.